Good evening. Today let us try to prove the binomial theorem. We know what is binomial theorem. First of all, it is binomial theorem because it contains two terms a and b, and this is raised to the power n. When we raise a plus b to the power n, we get a nc naught a to the power n plus nc1 a to the power n minus 1 b plus nc2 a to the power n minus 2 b square plus nc3 a to the power n minus 3 b cube plus etc. etc. So, last term is NCN b to the power n. Actually, in between we can have a term NCR a to the power n minus r b to the power r, which may be very useful for you to solve the problems. This year we have reduced portions, so we do not have that kind of problems. So, here very easily you can just see that a plus b to the power n is NC naught in the first, NC1, NC2 is there in the second, NC3 is there in the third, and so on up to the last is NCN. A to the power n is the first term for a. A's power is reducing by 1, n minus 1, n minus 2, n minus 3, etc., etc., and last a to the power 0 it becomes. In the first place we have b is 0, the index of b is 0, and the b goes on appearing, that is its index increases by 1. Here it was b to the power 0, then here we got b to the power 1, b square, b cube, and so on up to b to the power n. So, this is what we have to prove, and we know that we have to prove this theorem by mathematical induction, and this theorem carries around 5 marks. So, we have to prove this theorem by mathematical induction. You know that mathematical induction has 3 steps. It has three steps. One is verification. We have to verify that whether the property holds good at least for one term. We will take one term, and that is n is equal to 1, and check whether the property holds good. Then assumption. In assumption step, we prove that we assume that the property holds good for p of k, where k is less than n. We are not assuming all the natural numbers. Somewhere less than n we are taking a value k, and we are assuming that the property holds good for p of k. In the third step, we are going to do the proving, and in the proving what we do is we prove that it holds good for the next term also. That means we assume for k, and we show that it is true for next term k plus 1 also. That means if the property is true for 5, we will show that it is true even for 6 just by multiplying a plus b both sides. That is what we are going to do here also, and for this as see, this is the first step as it is. Verification, we have to verify whether the property p of 1 is true. A plus b to the power 1 equal to 1 c naught a plus 1 c 1 b. If you take only one term, we can easily see that the property holds good. In this place, if you put n is equal to 1, we get 1 c naught, and here we get 1 power 1, that is a, and thus immediately the next term we get 1 here, and 1 minus 1 is 0. So, a to the power 0 is 1, and we get b. So, we can very clearly see that the property holds good for when n is equal to 1. So, the p of 1 is true. So, that means the verification is done. That step is done. Verification step is done. So, we have easily proved that the property holds good for p of 1. That means p of 1 is true. In the second step, what we do is we have to assume that the property holds good for we have to assume that the property holds good for k, p of k. So, a plus b to the power k is equal to k c naught a to the power k. Whatever n is there, we can replace it by k, and we will get this step. So, it is continued now proof. We have to do that proof. So, actually we have to show that the p of k plus 1 is true. That means we have to show a plus b to the power k plus 1 is equal to k plus 1 c naught a to the power k plus 1 plus k1 c1 a to the power k plus 1 minus 1 plus k plus 1 c 2 a plus a to the power k plus 1 minus 2 b square, etc., etc. we have to show. Further simplifying these terms like plus 1 and minus 1 will be cancelled, and here plus 1 and minus 2 will be cancelled. So we get actually we have to prove these steps we have to prove. So for this, what we are going to do is, we are going to take up to prove that p of k plus 1 is true. We have to consider a plus b to the power k into a plus b. We already know what is a plus b to the power k. In the previous step, we can just see that we have got what is a plus b to the power k in the assumption step. So here we have in the assumption step we have this. Same thing we are taking into one more time a plus b we are going to multiply. That is in the proving step we are going to do now. See here, a plus b to the power k into a plus b we are going to multiply. That is actually a power k plus 1. If you see, a to the power m into a to the power n is a to the power m plus n. So k plus 1 this is. So this is a plus b to the power k is from the assumption step we have so much into we have this a plus b. So in this step what we are going to do is, we are going to multiply all these terms by a once. All these terms by a, this a, and this plus is here, I have put it here, and all these terms by b also. We are putting all these terms by b, and we get like this. After multiplying, we are going to multiply here. We have multiplied here with a for all the terms with a and all the terms with b. When you multiply, you will get like this: kc 0 a to the power k plus 1 plus kc 1 a to the power k b, and so on. You can see like this. And here also we are getting when we multiply by b, all these are to be multiplied by b, and we get like this. When you multiply by b, you get all these terms, and when you can clearly see that when you shift the b, the product that we got by multiplying by b, when you just shift it slightly, we can see that these two are coinciding. And we have discussed about this kcr plus kcr minus 1 is k plus 1 cr. There is a property like that, and in the Pascal's triangle we know that anything c0 is 1. We can see in that Pascal's triangle the left side slope was full of 1 only, that all that 1 is got by 0c1, 1c0, 0c0, 1c0, 2c0, 3c0, like that. Everything is c0. Anything c0 is 1, we know from Pascal's triangle, and anything c same thing is also 1, we know from the other side of the Pascal's triangle. Their other slope also gives you 1, and that is because anything c same thing is 1. So these three things we are using here, to rearrange the like terms. See, these are the like terms. We are arranging the like terms and also making use of these three properties. What we can do is, instead of writing kc0, we know that anything c0 is 1. So instead of writing kc0, we can as well write k plus 1 c0. And in the last one also, we know that kck is 1. So instead of writing that, we can as well write k plus 1 c k plus 1. And here these terms in between, you know that we can use these properties, and we get like this. So without breaking our head, we can just write this last step and conclude the theorem, because we know all these are going to be true. So nobody expects you to remember all these things. You have to just write this statement, rearranging the like terms and making use of the properties. K is 1 and kc0 is 1, and this one also kcr plus kcr minus 1 is equal to k plus 1 cr we get. If you write so much, we will get this theorem. Thank you.